For those of you that don't know me, I'm Stefanie Milam. I'm at NASA Goddard Space Flight Center. So I'm going to introduce the next session, our last session. But after all the presentations we had yesterday, I can't help but actually present a little bit on actual comet science, because that's what I do for a living, as well as a bunch of other things which you probably have picked up over the course of the last day. So what I want to talk to you about is a little bit of introduction to what our last session is. Our speakers yesterday afternoon actually gave us a great, sort of segue into our last session, introducing you to planetary atmospheres, both within and without, for endo and exoplanets is what we like to say. But what we're going to talk more today about is actual planetary missions and sample return. This is really important. This is actually going to bodies in our solar system or analyzing materials that have been returned from bodies in our solar system are really good insights into what we can learn about the actual cycle of matter, where our interstellar inheritance may or may not have come from, but also things like how much chemistry is actually happening within our own solar system and if there's possibility for life. So this is just another version, I'm sorry it's so dark, of what you've already seen. So the stellar life cycle, where stars and planetary systems form from diffuse clouds, which collapse and condense into denser clouds and cores. We had a whole session on disk chemistry. These disks start forming planetesimals, and then stellar systems are formed where we have things that are comparable to our own solar, well, turns out they're not so comparable to our own solar system. But this is where we can actually start studying whether or not this process has any preserved material, recycled matter, and how that may contribute to not only our own solar system, but also other solar systems. So is that chemistry ubiquitous across all star formation, all planetary systems, or is there something special and unique about our own? This is the same picture that you've already seen. I figured I had to show it this morning because you saw it like 5 times yesterday, and I don't think anybody else is going to show it today, so I had to put it in. But basically, this is giving you the whole concept of what we're trying to do. We're trying to see how much is actually happening in the chemistry of these things that we're finding all over, the galaxy now, and hopefully in other galaxies at some point. But whether or not this material is actually preserved, and what we can do, and how we can try and determine what chemistry is actually happening, and if we can actually bring that back to home. What we can analyze in a laboratory here is so much more sophisticated than what we can do remotely or even in situ. So there's things that we actually can learn about this whole process and what's going on just by bringing samples back to Earth. Okay, so here's the eye chart. The known molecules, actually this is only some of them. There's over 200 now. What Paula actually showed you yesterday was that most of these are actually organic. That may be a bias of our own, but so far it hasn't proven to be so. We have looked for non-biological molecules. We've looked for metal-bearing molecules. We've looked for silicate-bearing molecules. What we're seeing in the gas phase and the chemistry in the ISM is actually very organic rich. Sometimes it's a little more extreme. We have ions, anions. You heard all kinds of crazy things in Eric's session in the morning yesterday. But in general, it is organic chemistry. And that's something that's really what we need to bring home is we have this rich organic chemistry. And right now we're at the limit of detection. So how much of that organic chemistry can we actually detect? So what we try to do is we try to look at what our interstellar inheritance is actually from. So as you heard a lot yesterday, comets are considered some of the most pristine objects in the solar system. In general, small bodies in the solar system are considered pristine. So that includes asteroids, which will then, when they hit the Earth, are meteorites. And even some captured satellites, so small moons in the outer solar system are even considered to be very pristine. So before the Rosetta mission, we actually were pretty limited to what we could actually study of comets. We have to wait for them to come by. They have to be big and bright. And so what we do is we basically exploit every telescope we can whenever we have a good comet. This leads to lots of observing proposal writing. On average, I think I submit about 30 a year. But that's okay. That's what we do. And so we are in this realm that we can only observe what we can observe because they're short-lived. We don't get to stare for hours and hours and hours or weeks or months or even years at some given disk across the galaxy so that we can integrate and try to get a better signal of noise. We have a comet. It's here for a couple of weeks when it's at its brightest, and we have to do what we can to try to detect what we can. So this was what our inventory looked like sort of right before Rosetta. We have a lot of the same chemistry, a lot of the same ices, as Reggie showed you. This all looks like it's the same. But we also know from Stardust, which was a mission that flew through Comet Comae and brought samples back, that there's a lot more chemistry that's going on, and there's a lot of processing that's actually happened in these bodies. We know that they're very mixed. They contain things that are from the inner solar system where it was extremely hot. A lot of processing happened. But it also contained things like amino acids. So Jamie's going to talk to you about the detection of amino acids in comet samples. That also indicates that there is some amount of that material that's preserved. And we heard a lot about isotope ratios and other things that comets have in them. But the key is there's a lot going on. It's not something that we can just get a sample from. We're like, oh, it's preserved, and it's going to tell us our whole story. We have to actually understand the chemistry in comets themselves. There's a lot of material. There's a lot of things going on. Catherine got into some of the details of this yesterday. We have all kinds of mixing. We have thermal processing. We have radiation. We have shock chemistry. We have actual ion molecule chemistry that happens. There's cold regions. There's hot regions. And actually, comets contain all of this. So how much is pristine? How much is preserved is the big question. OK, so what we're trying to do, we're trying to basically take what we can do in a laboratory here on Earth, where we have sensitivities that we can do parts per trillion detections, right? Very complicated molecules, things like amino acids, prebiotic molecules, sugars, nucleobases, et cetera. And we want to put that back into the simple chemistry that we have now in the interstellar medium. We're getting there. We have a comet sample return. We have asteroid sample returns now. In fact, if you've been following anything on Twitter with the OSIRIS-REx mission, they're approaching it. They're about to go and collect sample from another asteroid in our solar system and bring it back. It's all very exciting. In fact, 2 people on that team are here today, so they can tell you more about it. But this is what we're really striving to do, is we want that simple chemistry to go into this complicated chemistry, because then we can then assume that the interstellar ubiquitous chemistry that Paula has showed you is actually going to have something that's comparable to these kinds of things. Unfortunately, we can't go to every small body in the solar system. We're a little limited. These are the comets that we've actually visited. There's only a handful. Hopefully, we'll go to another one. Actually, the same one, but another sample return mission. But most of these are in situ observations, actually all of them except for 81P, which was a sample return from Coma. We don't have that good of statistics. We can't go to everything. So what we are dependent on is remote observations so that we can put these things into context. So what we do with remote observations is we take our radio telescopes and we point them at the sky, and hopefully we have a lot of bandwidth and we have access to all the telescopes in the world, and we get a bunch of squiggly lines. We do our magic, and then we can say, oh, look, we have abundances, and they compare to things, and sometimes we know what that means, and sometimes we really don't. This is not an easy thing to do. Yeah, there's comparisons that we can make, but again, it's one comet, 2 comets, maybe a dozen. So how we can actually extrapolate from general populations, because comets come from different regions. Some of them have been around the sun more than others. This is a big extrapolation, but it's all we can do for the moment until we get more and more numbers. D over H is an even more challenging question. Actually, there was an article in Astrobiology that was just published this morning about potential source of Earth's water. I haven't got to read the whole article, but what I read on the Metro was pretty interesting. So they're even still questioning whether or not comets could have been a main contributor. But we can't say yes or no because we have very limited statistics. So we're still working on doing things like this. Access to water lines in space is something that we really need. So developing new space missions that follow up things like the Herschel Space Observatory is something that would be really useful and beneficial to not only cometary scientists, but actually all astrochemists. So the Origin Space Telescope is a mission concept that's being worked on. I couldn't give a talk without saying something about ALMA. My team has basically led all the cometary studies with ALMA. So we've actually observed about 6 comets now with ALMA. This is some of our first results. And basically what I wanted you to take away from this is there's actual chemistry that happens in the coma. So just because we're seeing something remotely doesn't mean that that's the pristine actual material. Things are actually happening within the coma itself. So what you're seeing here is the spatial distribution of these molecules for a given comet. So this is comet Ison, this is comet Lemon. And you can see that they're very, very different. Agency is probably being formed through jet activity or some other mechanism. Formaldehyde, we think, comes from very complex organic polymer-like material. That's chemistry. That's not pristine material. So actually deciphering what these things are is something that's quite complicated. But we have access now to new facilities that's going to help us. And every once in a while, we get to go to a comet, and we get to do things like in situ sample analysis. So you heard a little bit about the Rosetta mission. It was fantastic. We had mass spectrometers. We were there for a couple of years. We crashed 2 things on the surface. The spacecraft itself, as well as the lander. The lander crashed. Glycine was confirmed after the preliminary detection that was made with stardust. What we then can do is take all this great mass spectroscopy, put it back into context of what we can do with remote observations, determine what that chemistry is, see if there's any variation or differences, and do things like isotope measurements that are really challenging to do from the ground. And also, if there's a future sample return mission, then again, we can do even more detailed studies. So the CSER mission is something that's been being proposed, which would bring not only solid samples back from a comet, but also the volatile material. And of course, I work for JWST, so here's my JWST slide. JWST is also going to be revolutionary, giving us access to things that we can't do from the ground. And this is a mission that's actually being built. So we have access to all kinds of different organics as well as water, but most importantly, carbon monoxide and carbon dioxide. These 2 molecules are something that we can't resolve with current infrared space telescopes, such as the Spitzer Space Telescope. So knowing these abundances is actually a very key thing, as well as if we can actually get isotope ratios. So why do we care what all this stuff means? Well, there's some impact that it could have on life, delivering organics or other materials. There's all kinds of stuff that falls down on us. 10 to the 7 kilograms per year has been estimated that actually rains down on Earth every year. That's about 700 African gray elephants. It's a lot of elephants. And then again, what's actually pristine and what's not? And what are we studying? What are we learning? And what's the chemistry we can actually extrapolate from that? This not only happens to Earth, it happens to everything in our solar system. We actually see impacts happening routinely across our solar system. So this is the Shoemaker-Levy impact that actually hit Jupiter. We can still see cometary material in Jupiter's atmosphere. We are still observing that today. All right, so moving on. So basically what I want you to take away from this is what we can do in the solar system is basically get tangible insight into interstellar chemistry, the processes that happen during planet formation, not only in our own solar system, but that we can then apply that to disk or planet formation across the galaxy. We can do detailed studies on unique chemistry that may be or probably is actually occurring in real time throughout the solar system. So comets have real chemistry that are happening. We now have resolution and sensitivity with telescopes and flyby missions, et cetera, that we can actually see that chemistry happening. And it provides a ground truth. So if we can actually go to things, bring back samples, that's a ground truth for what we can do for remote observations. But we can't go to everything, so we still need to have some sort of global context. So this session is going to talk a little bit about doing laboratory analysis of primitive bodies, so meteorite and comet analysis. We're going to talk about Mars. We're going to talk about doing actual field work, so searching for habitability in extreme environments across the solar system. And then we're going to talk about Pluto and then some of the small satellites across the solar system.